let me introduce Dr. Siegfried Fassel, the head of Moving Picture Technology at Fraunhofer IIS. He holds a doctorate in electrical engineering and teaches technology studies at the University of Television and Film, HFF, in Munich, Germany. His general research is directed toward image and video processing for broadcast and movie production. He chairs multiple national and international standards bodies and is a SAMTE Fellow and IEEE Senior Member with several publications in image and video coding, media over IP, 3D image reconstruction, and AI-based production tools. Also on stage is Dr. Enno Littman, Managing Director and CEO of IHSE. After gaining his PhD in the field of neural and applied image processing and robotics, he held several senior research and management positions in the electronics industry. Before becoming program director at Galileo's IOV satellite navigation program, he held the position of a NATO advisor for the integration of UAVs into manned airspace. In 2008, Dr. Littman joined IHSE Germany, and in 2016, he was named Managing Director and CEO for the company. During his time at IHSE, he has been instrumental in the development of low-latency KVM switching systems for both uncompressed and network-based KVM. With this, I will turn it over to Dr. Littman to kick off this session.
Thank you, Rachel, and welcome everybody to be here and listen to our take on JPEG-XS. And of course, your first question might be, why are we both here on stage? And we will motivate why Fraunhofer and IHSE are well suited to talk about JPEG-XS. And I would ask you, Siegfried, to start off. So why is Fraunhofer specially suited for this?
Sure. You may know Fraunhofer. Maybe Fraunhofer is the largest research organization in Europe with about 30,000 employees. And 5 of the institutes are working in the business area, digital media. And of course, we are more or less involved in all standardized audio and video codecs. And we always look what is the next codec which we are looking for. What is the next interesting part which is missing in the media workflow? And that's the reason why, of course, we are working in different standardization bodies and looking for new things. Especially, you may know, of course, IHSE, who is more focusing on video distribution codecs like H.266, 4, 5, 6. My institute is more working on audio technology and also video codecs for professional applications. So the background here is first digital cinema, JPEG 2000, and now we looked to a new technology for video production or live contribution. And that's the reason why JPEG-XS was developed in the first place. Yeah, that's why we are here. And we want to give you a little bit an insight, of course, of JPEG-XS. You might have seen a lot of banners which know JPEG-XS, and we can give you today a little bit of more deeper insight why JPEG-XS is so good.
Thank you. And now it's why is IHSE here on stage? And obviously, it's not obvious, right? IHSE is not a company that normally provides IP cores, but we write IP cores actually for all these years that we're doing KVM technology, because all the KVM manufacturers had to provide some kind of video codec for the video transport. So we have a long-standing experience in doing that, and that helps a lot. Of course, we have a long-standing collaboration with Fraunhofer, and we already implemented and exploited the FPGA codec called Litchi, which is one of the, predecessors of the JPEG-XS codec. right? And on top of this, of course, we have an infrastructure around the video codec. So it's interesting for us not only to transport video, but to transport together with it data like USB, like HID, like audio, and so forth. So we really apply it, and we have a close knowledge about what is needed beyond the pure video transport, and that comes to bear on our implementation of the video codec JPEG-XS. So maybe we take the next step and now ask us, why do we look at JPEG-XS? Why don't we look at H.264? Why don't we look at H.265, other than it's not developed in your shop?
Sure. As I mentioned before, I mean, within the last 10, 20 years, of course, it was always a goal to improve the compression efficiency of video codecs. However, this comes along with increased complexity. That means if you look today to an H.266 codec, probably the encoder is 100 times more complex like the decoder. And of course, this is useful for distribution, for streaming, where you have to code it once and then consume it multiple times. But if you want to use it for live production, if you want to use it really for transmission lines, then it's much too complex. On the other hand side, the video codecs today mainly are addressing 420 or 422 and not the highest bit depths. And if you want to, you can do this also, of course, with higher bit depths, but then you need really, really big computing power. And that's the reason why we said, okay, we need something which is tailored to the needs of the video production industry. And tailored means in this case, it has a low complexity, means it can be used in different platforms with lowest amount of resources. And what is also important, especially for live contribution, is that the latency is very small. So that means we cannot use cube of pictures, so that we have 15 frames delay. So that means in this area, we wanted to have a sub-frame latency. And that's the big benefit of JPEG-XS so far. And that's one of the key features why we developed this.
Okay, and now the question, why is JPEG-XS specially suited for KVM applications on top of the features that we've already seen? Right? Closer? Okay, good. So first of all, it's a lightweight codec, which means that it can be easily implemented into an FPGA type processing, right? And of course, KVM shouldn't be the most expensive part of a video production site. So we have to do something which is efficiently implemented, and still it needs to somehow talk to the broadcast video streams, right? And this is maybe for the first time, I haven't seen any SDI-based KVM switcher ever. Yeah, you see video switches with SDI, and you have seen KVM switches that are routing usually proprietary protocols. But now with the JPEG-XS, it's evenly suited for video and streaming transport as much as for KVM purposes. That means that in future we can have broadcast workflow, broadcast streaming talk to the KVM world and vice versa. And also, if you remember SDI, that was a 422 codec. It was kind of a little bit limited with a color depth in that sense, and it had its own standards, while KVM was supposed to do the full 444 transport with up to 12-bit color depth, and this is now available with the JPEG-XS alike for broadcast and for the KVM part, and therefore it's specially suited now to unify the both workflows on that kind of compatibility level, right? Okay.
Yeah, maybe I can tell you a little bit about the history of JPEG-XS. So, as you mentioned, in the beginning, we started with a codec called Litchi together with you, and developed a KVM extender. The main goal here was really to have this 444 and higher bit depths and also a low latency. But at some point, of course, we saw that an interoperability might be also useful, especially if you want to transfer this codec to the broadcasting industry. And that's the reason why we started with an ISO, a new standardization effort called JPEG-XS. And here we defined quite good requirements in which way we can use it for different applications, different industries. And of course, KVM was one of them. Broadcasting was another one of them. And here we really had the main goal that it can be used on all platforms. Means it should be parallelizable, so that it can be used on today multi-core CPUs, on GPUs, but also on FPGAs. And that was a little bit a lack of the previous codec, that it was not able to parallelize it. Also, JPEG 2000 cannot be used in a parallel way very efficiently. So that means it mainly uses sequential processing. But with JPEG-XS, we could split it up. And that's the reason why it's today also very good for FPGA implementation. You have a good parallelization implementation. You can use it and directly implement it in FPGAs. And I think that's the benefit why it's also good for you. Of course, you can implement JPEG-XS on CPUs, but of course, still you need multiple cores. In an embedded device, however, you need an FPGA. And that's, I think, why you are especially so interested on FPGA implementations.
Well, and these days, really, we all think about energy efficiency. And of course, if you use a CPU, then you will have all kind of, say, side consumption of energy in order to run the whole algorithm, and you need quite powerful CPUs to do that. While if you're doing FPGAs, it's a very good compromise as opposed to ASICs, right? Are we talking ASICs about JPEG-XS? Yes, we are. There are efforts to put it on an ASIC, and then of course that's very energy efficient. It's even cost efficient to do it on an ASIC, but JPEG-XS is still a young algorithm, and we will see improvements over the next couple of years. We will talk a little bit at the end about it, and these improvements can easily be implemented then into an FPGA, and therefore we believe FPGA is right, the good platform for an implementation, especially in an environment where customers might have different requirements, and FPGA implementation can be optimized with regard to the usage of FPGA resources to allow for additional applications being put onto the same FPGA. So, and what makes us believe that this is the new standard then?
Yeah. As I mentioned before, it is really a tailored codec. That means, of course, we have now 20 years or more experience and know-how in video codec design. And you know in which way you can use entropy coding, prediction, motion compensation, and so on. But at the end, the question is, what is the best trade-off so that you can use it in your applications? That's the reason why we said, okay, we want not 100-to-1 compression ratio. It should be good enough so that we can compress it, let's say 10-to-1, 15-to-1, so that we can go a magnitude of order lower in the bandwidth. But on the other hand side, keep the complexity and latency as small as possible. And I think that's new in the video codec development arena, that we do not target really the highest compression efficiency, but really design a codec especially for a specific use case.
And so JPEG-XS turns out to fulfill all these requirements in a very special way, right? I mean, everybody who is busy or is involved in broadcasting knows that a 4K 60 image in say standard transport will require 12 gig of bandwidth. And we're all talking now IP transport, of course, right? So what does that require? If you want to transport 12 gig of data, then you need switches which support maybe the 25 gig standard or even more, or you have to refer to a light compression anyway. So if you do that anyway, then you can take this JPEG-XS step now, and that brings down the 12 gig bandwidth to a 1 gig or below 1 gig bandwidth, and allows you to refer to the standard 1 gig network world, which is out there everywhere in the world. And the good thing, as Siegfried already mentioned, if you have higher quality requirements, then you can brush up the quality by just using maybe 2 gig or maybe 5 gig of the bandwidth. So you're really flexible in accordance with your requirement that you are implementing at that point in time.
And what is also important, of course, is that the world goes, or the trend is in direction Internet protocol. That means today we want to get rid of SDI, we want to get rid of dedicated transmission lines. It might be okay still for 4K, but for 8K anyhow, you cannot use really good coax cables or SDI. You have to use either 4 cables in parallel. The cable length will be reduced because of the high bandwidth, and that's the reason why IP is very important and efficiently. And of course, also the workflow is very important. That means today you want to have a closed workflow where you can capture from the camera over different switches to the post-production, send it to the cloud and back. And that can be done only if you have one seamless IP transmission line. And for this reason, we also developed a lot of side standards, I would say, not only JPEG-XS. So we worked also in the IETF on an RTP standard. We worked also in the VSF on technical recommendation, in AMBA on NMOS for orchestration and registration of devices, and also in SMPTE on MXF file transport. So we have today now a complete suite of standards which, let's say, allows to implement IP transport very easily. And I think that is very helpful, so that today we can have a seamless workflow in place.
And if I may add to this, with the availability of all these side standards, the system integrator task will become become easier, basically, because you have all more standardization, you have more monitoring tools, you will be able to request information from transmitters, from receivers, independent of what they provide in function. So it will be the same for KVM, it will be the same for broadcasting. So there's a lot of better handling of data streams to be expected in the future. And just to conclude maybe what we are saying, can you give us an outlook of what's to come in next editions of JPEG-XS?
Sure. So we already worked on different editions of JPEG-XS. The first edition was the classical broadcasting, so having 444, 422, up to 12 or 16 bit per component. The second edition we worked on, which was published last year, was CFA Bayer pattern, so that we can compress directly from the sensor to an IP stream. And the third edition, which comes now within the next 2-3 months, adds a frame buffer so that we can predict the image from the previous frame. Some companies call it FEP, but in principle it's a temporal differential coding, which is now part of the edition 3 of the JPEG-XS standard. And you can see on this slide a little bit the difference. On the left-hand side, you see a natural image where some people playing on drums. So there's not so much, let's say, static inside the image. So, however, still you get some dB of improvement. On the right-hand side, however, you see a mixed or screen content. And here, if you have windows where you are playing video, and on the rest you have a text screen or other elements which are static, then you can have an improvement of 5 to 10 dB. So that's really big. Either you can then increase the compression ratio, or you have a very high quality. And we saw it even in medical applications. If you have a medical image, for example, and this stays on the screen, you can have a lossless display after 3-4 frames, and that is really helpful. And I think this is especially also for KVM extender, of course, very important, because here typically you have a kind of mixed screen or screen content, so which is not always moving completely on the screen.
And that obviously shows that we're looking into a future of a tunable video codec for KVM applications, which will give our ultimate customers a better video transmission with less bandwidth and interoperable with their broadcast streams. So we believe that will be the future between video and KVM in broadcasting. Thank you for attention, and of course we will take a number of questions if you have any. Thank you. Yeah. Any questions?
The TDC mode here, is it already an ISO published spec?
Sorry, can you repeat?
The time differential coding method here, is it an ISO published spec?
Yeah, as I mentioned, it's in the edition 3, and the publication will be done in some months. So it's still already balloted, but you know, ISO needs sometimes some time to publish it, yeah. But it's ISO standard, yeah.
Any more questions? Okay, then thanks again for coming, and see you next time. Thank you.